There we go. So we should now be recording. I'm going to go ahead and share my screen real quick. And so I'm just going to go to preview here. So there's just 3 questions. Question 1, what is light? So this is a very classic derivation in electromagnetism that I think like everybody should have to go through at some point if you're going to do any sort of E&M related class. So it's a very straightforward derivation, and I did the derivation in the lecture. I was debating whether or not to kind of make this a homework problem. I decided we'll just do kind of together in class. And then we're going to show how the solutions satisfy the Helmholtz equation. So, or how this solution up here in the time domain, when you do a phasor domain equivalent, you get a Helmholtz equation. And then that similar thing, how you can show that some generic plane wave thing will actually satisfy it. So I'm going to stop sharing now, and we're just going to go to, I'm going to pin my video here on the little worksheet here. So step 1, we just have Maxwell's equations. Del cross E is negative partial B with respect to T. So you notice I'm using time domain here. We are not sinusoidal steady states. So all these J omegas are actually d by dt's here, time derivatives. Okay, so we have Faraday's law, Ampere's law, and you notice there are no sources. So whenever you hear the word source free, like that, source free, those are kind of key buzzwords. Sorry, my monitor, my brightness is flickering. So maybe if I kind of do that, there we go, that'll stop it. That'll make it a little more tolerable. So when you hear source free, that just means your charge density is 0. So there's no free charges anywhere, and there is no current. So the no current here means in Ampere's law that that little mu naught J term is gone. And we're also going to say del dot E is equal to 0 now. Normally there'd be a rho over epsilon naught here. And then del dot B is equal to 0. So the question now is prove the existence of a wave from these equations. So I kind of love this exercise because it's basically saying here are Maxwell's equations. Here is just how Faraday's law, Ampere's law, and electric and magnetic fields doing their things. Given Maxwell's equations, prove the existence and nature of light itself. And it only takes like 3 steps to do this here. So I think this is just one of the most profound insights in modern physics. But it kind of gets overshadowed a bit, but I think this is kind of amazing here. So what we're going to do is step 1, take the curl of Faraday's law. Just like so. So up here, we're just going to take the curl. So you have del cross E is equal to del cross minus partial B with respect to T, like so. Oh, sorry, del cross. So I just went up here and I put a little curl on both of those terms. So fun fact, the derivatives here commute. So I can actually write this as negative partial with respect to T times of del cross B. So that's just a fact. If I do 2 partial derivatives, it doesn't really matter what their order is. And the curl is just a very fancy collection of a bunch of partial derivatives. So this is a very straightforward step you can do. You then look at this and say, oh, I know what the curl of B is. It's just Ampere's law up here. So what you get is negative partial with respect to T of mu naught epsilon naught partial E with respect to T, just like so. So remember, every time you see the little arrow there, that means it's a vector. So I hope I will be consistent with that. It's easy to forget. So again, these are just constants, so we can smish-mash them. Now I'm going to write this as negative mu naught epsilon naught times partial squared E with respect to T squared. So that's a T there, a little T. There we go. So then this curl guy here is kind of a problem. So let's write that out here. Del cross E. So fun fact, in vector calculus, you may or may not have been told this, but you can look this up. There is an identity in vector calculus which says the following. The curl of a curl is equal to negative vector Laplacian plus del dot E. So this is true for any vector field whatsoever. It is just a mathematical identity that this operation here is equivalent to this operation over here. I thought about making it a homework assignment to prove it, but it's horribly tedious, but you can do it if you just plug in the definitions and you get the same thing with here. So you may have been exposed to this if you had a good vector calculus teacher, and they probably did not explain to you where it would come in handy ever. But this is just an identity that if you took vector calculus, hopefully, fingers crossed, you got some exposure to it at some point and you proved it. But this is just, you can look it up. This is just one of those true things like all those famous trig identities that you've seen before. So then we just plug it back in, or sorry, you notice this term here, the gradient of the divergence of E. Well, I assumed a source-free region. So we're just floating out in space. There's just electric and magnetic fields. There's no free charges and there's no free current. And since del dot E is 0, that means this guy here just goes away to be a 0 here. So what you're left with at the end of the day is negative del squared E is equal to negative mu naught epsilon naught times partial E with respect to T squared. So obviously the negatives just go away. And fun fact, this is a wave equation. More specifically, it's a vector wave equation because this is a vector Laplacian operating on a vector field. But if you remember from your partial differential equations, you just have the second derivative in space is proportional to the second derivative in time. That is a wave equation. And this constant here in front is actually 1 over the phase velocity squared. So I'm gonna give that a name C naught, like that. So what you get is, just kind of move this off to the side. So you have a del squared E is equal to 1 over C squared partial squared E with respect to T squared, where C naught is 1 over the square root of mu naught times epsilon naught. Sorry, you can see that. So I just kind of summarized it over here on the side.
Question about the negative sign canceling. How did that occur on the left side over there?
Oh, because if I have, negative x equals negative y, then you just have x equals y. I just got rid of both negatives.
Oh, I see it above. Sorry about that.
So there you go. That is a vector wave equation. So you just started with, sorry, my camera's a little off here. I can get it all in the frame. So you notice we just started with Maxwell's equations. We just assumed there's no sources, no charges, no current. There are just electric fields and magnetic fields floating around in space and using nothing but Maxwell's equations. And like this barely 3-step derivation, we got a wave equation on the electric field. And if you do the same thing, you can actually repeat this derivation. It just, instead of taking the curl of Faraday's law, you take the curl of Ampere. It's the exact same thing, because you notice you have a curl with a time derivative, curl with a time derivative. So you just flip-flop the order and do it on the B field. So we'll write this down here. So by a similar argument, you also get del squared B is equal to 1 over C naught squared partial squared B with respect to T squared. So the same argument will also give you this. So I have electric fields and magnetic fields satisfying a wave equation. And those waves happen to propagate at this particular, oops, let's move that back here, get this all in frame, at this particular little velocity here, which just so happens to be 2.99 times 10 to the 8th meters per second. So buried within, oops, sorry. So right there, buried within Maxwell's equations, we have a wave equation that predicts the existence of electromagnetic waves propagating at this speed, which we now, with the benefit of hindsight, we know that that is the speed of light. And so all light itself now we have proven is essentially this electromagnetic wave. Now there's a few extra little properties we haven't quite derived. For example, it's a transverse electromagnetic wave. So there are many solutions that satisfy these two guys individually, but you also have to satisfy Maxwell's equations there. So what you get are the transverse electromagnetic waves. So usually, by convention, we're going to say that z is the direction of propagation. And let's see, I'm going to call this x hat and y hat here. So it'll be a right-handed coordinate system. And what you'll have, the waves may be propagating in some particular direction like so. And if I have an electric field, say, that is oriented this way, so my electric field oriented along the z direction, my magnetic field would be oriented along the y direction, and then the direction of propagation would be down z. So this is why we say that it obeys the right-hand rule. So you point your fingers in the direction of the electric field, you curl in the direction of the magnetic field, and that is the direction of propagation. So that we call that a transverse electromagnetic wave, because the fields are perpendicular to the direction of propagation. So that's kind of an important idea, is this notion of transverse versus longitudinal, like that. So a longitudinal wave might be something where I have an electric field pointing this way and my wave is also propagating in that direction. Longitudinal waves are actually not allowed in Maxwell's equations. So that's kind of a subtle point. We're not going to prove it because technically the wave equation here will allow for them, but the nature of Maxwell's equations, they have to kind of simultaneously satisfy each other. And you can show that longitudinal waves are not strictly allowed when you're out in free space. That will sort of be a rule we bend a bit when we're doing waveguides, and that you will have one of your field components pointing along the direction of propagation. However, it's kind of a cheat because you can imagine, what if I have a wave doing this and I superimpose it with a wave maybe doing that? I have two transverse waves, but what you'll get is a net sort of flow of energy that way. And you'll also get some of your field components, like your electric or magnetic field might also have a little piece of it going in that direction. So it's kind of a cheat there that these individual transverse waves can kind of add together to sort of give you this pseudo-longitudinal component. So just kind of think about that. That's just some basic theory. We're not going to super harp on those sorts of things, but this idea of transverse versus longitudinal components is going to be a big deal when we do the waveguide stuff, because you'll have the transverse to the propagation and longitudinal down the waveguide, because there'll be a definite direction of power flow. Okay, so that is the first question in our in-class quiz. So we're just starting from Maxwell's equations, and we derived a wave equation. We haven't proven exactly the transverse bit, but that's not really something we want to harp on. Okay? So let's go on to the next question. Or sorry, unless there's a quick question, we can answer that.
Do we need to write? Do we need to copy all of that into the HTML?
All of this? Yeah. No, just kind of enough to show that you got the basic steps. Really, it's starting with here. This was given. It's these 3 steps here, and the conclusion is all I care about. Just show me that you followed along and got the gist of it. All this other stuff up here, you don't have to talk about. That's just me kind of, what's the word, philosophizing about electromagnetics after the fact. So let's share real quick. So that is the nature of light. So how do you feel? Does your mind just get blown? Hopefully. I think that's one of the best derivations in all of physics. So the next question is just to show how the wave equation in the time domain turns into a Helmholtz equation when you assume sinusoidal steady state. And this is just to reinforce this notion that a Helmholtz equation is basically just like a wave equation, but with complex numbers, assuming this kind of AC signal here. So where am I going to stop sharing? Okay. So question number 2, it basically just says, here is my wave equation. Del squared E is equal to 1 over C naught squared partial squared E with respect to t squared. So that is our wave equation that we just proved in the time domain. Next question is, what happens when we do sinusoidal steady state? So sometimes you'll see me just write SSS for sinusoidal steady state. Whenever you hear that, what it basically means is there is this phasor dependent of e to the j omega t. All time dependence has now been lumped into this sort of complex exponential, which also further means that all time derivatives are going to be replaced with j omega. So that's the only thing that fundamentally changes mathematically when you assume a sinusoidal steady state signal. So what that means is this, nothing really changes here. I've got this 1 over c squared. I have these two derivatives here, right? So if I do a second partial, all that fundamentally happens is this guy becomes squared. So you'll get a negative omega squared where anywhere you see that second time derivative. So you notice then this just becomes del squared E is equal to negative omega squared over C naught squared times E. So that omega over C should be kind of familiar at this point, right? We defined the propagation constant or wave number. We kind of use those terms interchangeably, which was omega over C for any sort of wave here. So that now becomes negative k squared. So all I'm going to do is just rearrange a bit, and you get del squared E plus k squared E is equal to 0. Just like so. So this, again, is just to reinforce that here is the wave equation, which you probably studied in your PTE class. But the Helmholtz equation is just a simplification of that when we're not in just generic time domain, but we're doing a specific single frequency signal. So I'll just make a little note. Here's Helmholtz equation, like so. This up here, just a little note, that's the wave equation. And this guy here usually has a special name. That is called the dispersion relation. So a fun fact, I'm not sure if we'll get in too much detail in this class, but the idea of a dispersion relation, it tells you how fast a wave will propagate as a function of frequency. So if you have a linear dispersion relation like this, it means all the waves are going to propagate at the same velocity. But that is not a general thing that is always true for all waves and at all times. For example, if you are solving something like the Schrodinger equation, you don't exactly get, you kind of get this Helmholtz equation too when you do quantum mechanics, but the waves don't obey this nice, neat dispersion relation. I believe when you're doing quantum mechanics, there's a square root of omega that gets in there. So what happens is, that represents different particles at different energies have different kinetic energies, and therefore they have different velocities. And that manifests as a nonlinear dispersion relation in their wave equation. So fun fact. So electromagnetics is kind of well behaved in that sense. But this again isn't exactly going to sort of always be true, because what you'll get is a situation where you maybe have a waveguide. And what's fundamentally happening in this waveguide is you have a superposition of two waves, where one wave is kind of going up like that, striking the top, and then coming back down again and doing this. And you just have this blob of energy that is actually these two waves kind of superimposed on each other at all times and throughout the entire thing. So you kind of draw it like this, maybe. It's kind of hard to visualize, but you'll sort of see when you do the mathematics of it. And so what happens is, depending on which direction this wave is, you get faster propagation of energy down the waveguide, or it might even slow down, because you can imagine the energy having to bounce up and down like this is going to sort of take longer to propagate down than a wave that's more kind of pointed straight. So depending on some of these wave numbers on your propagation constant, you actually get sort of faster or moving waves down your waveguide. So that's kind of an interesting result. For example, if you imagine a little horn antenna doing something like this. Let's see if I can draw a decent horn antenna. This is something you'll probably do if you get involved in a lot of radar applications. You might have this big waveguide coming down here, and different modes in that waveguide, or different types of solutions might represent waves kind of propagating up and down, or they might be a little faster, which means your energy won't all just kind of come out at the same time, depending on how you excite this thing. So some information goes faster or slower. This is also a very big problem in fiber optics. So again, you might have a little piece of glass, this long little cable like this, and this could be many kilometers long. And you have what's called multi-mode fiber versus single mode fiber. So a multi-mode fiber would be very thick, and the waves, the signals are actually going to be slowed down because the waves are essentially bouncing up and down like that. Whereas if you get down to, say, a single mode fiber, it may be doing this sort of thing. So what happens is you try and send a bit of information through something like this, and the energy sort of disperses out as it moves along, because different bits of the information are traveling at different phase velocities down your waveguide. So that's sort of just kind of whetting your appetite for future bits of information in waveguides. If you ever take something like integrated photonics, I think Steve Blair may or may not still be teaching it, you'll deal with this kind of problem as well. So we're going to introduce a lot of the mathematical fundamentals of waveguides. We're not going to actually touch fiber optics per se, but the ideas are very much related. Okay, any questions there before we move on to the final question? So on question 3, I'm going to,
I have a quick question before we leave the topic.
Mm-hmm.
You mentioned the dispersion. You mentioned the K dispersion relation. It's important to the Helmholtz equation. I mean, what was our initial motivation to simplify the vector wave equation into the Helmholtz equation to demonstrate conservation of energy?
So what was our motivation to go from the wave equation to the Helmholtz equation? Is that what you're asking? Because this represents a single frequency, which most of the time you will have like maybe a very narrow band signal, because the solution up here can be thought of as a superposition of the solution down here at just different frequencies. But that's kind of a good question. Mathematically, it's a lot easier to work with a single frequency solution than a generic time domain solution. And most signals are going to be relatively narrow band, and you can always kind of jump back and forth between these using kind of like a Fourier transform relationship. But mathematically, the Helmholtz equation is a lot more easy to work with than a full-on wave equation, precisely because you have basically this extra derivative you have to worry about, where here it's just spatial derivatives plus this sort of constant here. And then there's this implied time dependence. So at the end of the day, this is going to be a lot easier to work with and solve than kind of a full-on time domain thing.
So in mathematics, when they often tout eigenvector, eigenvalue problems or solutions, or I don't know, they tout the power of that. I suppose this is an eigenvector, eigenvalue problem. And it's easier to solve this than the time derivative version of that same problem, right?
Yes, if you just rearrange it like this, where you have some operator on your vector field giving you a scaled result of your original field, that's basically an eigenvalue problem. Eigenvalue slash eigenvector. You're still in kind of this continuous space, which makes the linear algebra a lot more complicated. But all sort of the mathematical understanding of these kinds of problems now applies to this sort of thing as well. So that's another kind of strong motivation to want to work in the phasor domain, is it puts it into a sort of formalism where there's already a lot of this well-established understanding.
Thank you.
But yeah, if you really want to think about it in those terms, that's good. We're not going to really emphasize this distinction though in this class. We're just going to kind of take this and run with it. And a lot of these ideas will pop up if you're like really fundamentally familiar with this stuff, but we're not going to really harp on that. as far as the class is concerned. Really, we just want to solve the waveguide problems and see what happens. So let's do another screen share. So the final question just says, here is an electromagnetic plane wave, some possible suggested functional form. I'm just going to write this down real quick. X hat E naught e to the minus j. Oh, sorry, that's a z hat. Let me write that. J kxx e to the minus j ky y. So the idea is, given this particular possible suggestion for a solution, is it a solution to my vector wave equation? Okay, so let's go ahead and run with that. Sorry, I wrote that down a little sloppily, but that's just a rewrite of the main thing. And we're just going to say k squared is equal to k sub x squared plus k sub y squared. So what this represents basically is, let's just draw some axes here. So here is my x, here is my y. So my electric field is polarized along the z direction, like that, but it's a uniform plane wave, say, propagating in this direction here. So you can call this a wave vector, k, and denote it with a little arrow like that. And you can actually write this as kx, x hat, plus ky, y hat. And that means this notation can actually be simplified if you express it in that sort of vector notation, because what you'll get is a z hat e naught e to the negative j k dot r. So it's the same expression here, but when you use a nice little vector notation, it kind of makes it nice and compact. So it represents a plane wave propagating in some particular direction defined by this wave vector. So you'd call this a wave vector here. So we had wave numbers and propagation constants, and so we call this a wave. So there isn't a propagation vector that I've heard of, but you could hypothetically call it that. So the only thing is, this expression here is just a sort of shorthand compactification of this longer thing here. And hypothetically, it could even have sort of a, an e to the minus j k z z in here, and this notation would still encapsulate all it. But we're not going to beat too much on that notion here. I just want you to kind of get used to this notation. So I apologize, it's a little sloppy. So let me just write that again real quick, nice and neat. So I have an electric field vector. It is a function of x, y, and z. It has a polarization, which I called it x again. I assume a polarization, so that's the direction that the electric field is pointing. I'm only giving it a single polarization, E naught, e to the minus j, k sub x, x. So the k sub x means it's the little x component of this wave vector. Then e to the minus j, k sub y times y. So these are the coordinate vectors here. So that, again, just that represents some plane wave where the electric field is polarized in this direction with my thumb, but it could be just propagating along in some arbitrary direction, moving along at the speed of light. So all we're going to ask is, does this thing satisfy the vector Helmholtz equation? So I'm just going to say yes or no, question mark, kind of like that. So here's the Helmholtz equation. Take this, sort of plug it into that. Do you get a true statement at the end of the day? So this is how you prove that this is a solution to this expression here. You just plug it in, and if you get a true statement, then you're just done. So the key here is the vector Laplacian. When it's operating on a vector, you basically get the scalar Laplacian acting on each individual component of your vector field. So you get del squared Ey y hat plus, can you see that? Sorry, I'm left-handed, so I have to put my hand in front, and I apologize if that's frustrating. I'm trying my best to not quite do that. I just, z hat, like that. So again, this, when the Laplacian operates on a vector, you get this whole kind of vector Laplacian output here. But when it's operating on a scalar field, like each individual little bit, then it follows a different rule. So we'll show that in a second. So first thing first, we know that I've limited my electric field to just a single direction. So that means this and this are both 0. So I will get del squared E is equal to del squared times the Z component of my field, Z hat. And then so the scalar Laplacian is going to be the following: the partial Ez with respect to x plus the partial Ez with respect to y plus partial Ez with respect to z. Oh, and these are all second partials. So put a little square here, like that. So that's this. So this is a lot less horrifying than it looks. It's just a bunch of partial derivatives on top of partial derivatives acting on a vector in every which direction. So you just have more derivatives on top of derivatives to just account for all the various components of your vector field. So that's why we kind of assume some of these simplifications, because if this is going to be true for this particular wave, then you notice we could flip-flop our coordinates and we can expect the same thing to be true at the end of the day. So we're just going to pick out a single coordinate here. Sorry, and then that's a z hat here, because this already had the z hat there. So again, that is the scalar Laplacian, which is just the partial derivatives acting on each coordinate. And then the vector Laplacian is a scalar Laplacian on each individual bit. So don't feel too bad if that's a little overwhelming. This is just to kind of get us to a happy place where we can solve Maxwell's equations. But first things first, since we're assuming a plane wave, this particular piece of my derivative is 0. There's no change along z, so that's going to simplify things a bit. But we still have these x and y dependencies to worry about. So you see I have an e to j kxx and e to j k minus j k y y, case of y y. However, so this is actually pretty nice because these are separable here and we're doing partial derivatives. And these are complex exponentials. So you just write this out. It's a little tedious, partial squared e. So this is the z component of e. And since this is the only bit of it, we don't necessarily have to keep writing that little bit. I'm just going to say partial e and just drop the vector on it because that's the only piece of it. With respect to x is going to be e naught negative j kx e to the, oops, sorry, I'm a little squished in here. Kxx e to the minus j ky y. So this is kind of the beauty of the complex exponential notation, is it makes all these derivatives very, very easy. And then of course, if I do this again, partial squared, oops, sorry, that was just the first partial. So take away those little squares. Now we're going to do the second partial. So sorry, just take those away. And now we're doing the second bit. And this jkx is just going to come back down again. So I'm getting e naught times negative j k sub x squared times e to the minus j, and I'm just going to write this as k dot r. So this guy here is very simple. Negative j kx squared is just negative kx squared. So the negatives square and kind of cancel out, and then the j squares to give me a minus 1. So I'm just say negative k squared e naught e to the minus j k dot r, like that. So by a similar argument now, we don't have to repeat that. We can just say partial squared e with respect to y squared is going to be negative ky squared e naught e to the minus j k dot r.
How did our k turn into a vector?
It was back up here. This is a shorthand notation for this stuff here. So that's actually a good question. I was worried whether or not some of you would be comfortable with that. So it's a very, very quick little thing. You say k is equal to kx x hat plus ky y hat. And you say r is a position, a coordinate vector. So x hat plus y hat, like that. So that means, yeah, k dot r just becomes kxx plus kyy. So you can see in the complex exponentials, if you have an e to the that, they become a product there. So this is just a nice shorthand to compactify that expression up there. Okay, so let's see, I'm running out of space, so I'm gonna just sort of bring us back up to here, because we're back here at the Helmholtz equation, right? So that del squared is going to be the summation of these two terms here. So you'll notice we'll get E naught e to the minus j k dot r, and there was a minus kx squared minus ky squared that came out of the del squared, plus k squared e is equal to 0. So remember, we defined this guy up here already. Oops, sorry, it's not quite in the view here. So this expression up here. So we broke our wave vector down into these x and y bits, which means this little guy here is just a negative k squared. And we also look at this and say, oh, that's my original E. So this should feel very familiar. I had you do this exercise a couple weeks ago with voltage and current when we had a Helmholtz equation, and I just said, here is a traveling wave down a transmission line, prove that it satisfies the Helmholtz equation. So we're doing the same thing. It's basically all the same derivation. The only difference now is we have vectors and multiple dimensions to worry about, which at the end of the day just manifests as a bunch more partial derivatives you kind of have to keep track of. But the solution at the end of the day was the same. We basically got negative k squared e plus k squared e equals 0, and that's a true statement. So that is your proof at the end of the day that any function with this particular form, where are we up here? Let's go back. So if I have any function that looks sort of like this, it will be a solution to this. So I'm going to just kind of connect these. That thing there is a solution to that thing there. And the moment you make that connection, a lot of things suddenly fall out very quickly. For starters, the Z polarization is completely arbitrary. It could have been another polarization, propagating some particular direction. So I could just flip-flop the Z with X and Y, and I would still have a solution. Any linear combination of solutions is also a solution. I can add multiple frequencies together or multiple waves together because the Helmholtz equation is a linear operator there. I can just add a bunch of solutions together and they will also be solutions here as well. And so that's a very key idea in PDEs and electromagnetism, is any linear combination of these solutions is also going to be a solution. Because that's fundamentally what's going to happen when we do our waveguide. So I've got a tiny little piece of blank space here. Let's just draw a quick little waveguide here. There's my top plate, there's my bottom plate. It's going to be separated by some distance d. There's going to be sort of the longitudinal axis down my waveguide here. So you imagine something like this, where this is a perfect electrical conductor on the bottom. Ooh, let's bring this up. And then I'll have a perfect electrical conductor on top, if we can see that. And the solution will basically be a wave. Let's see if I can draw this. It'll be a superposition between one wave going this way and then a second wave, sort of an equal opposite wave, going that way. So I have one plane wave kind of going up, one plane wave going down. I add them together. Each one of them is a solution. So their superposition is a solution. And they just so happen to satisfy the boundary conditions here that I want my electric field to be 0 at the top and bottom if you pick the right conditions. So that's the key idea here, is I have a general solution here. Any combination of things with this form will be a solution here. The only final step you have to add are boundary conditions. So that kind of ties into that original notion we talked about with the Helmholtz theorem, right? Where you know the curl and you know the divergence. You have a general form of your solution, and then when you impose boundary conditions, you get the solution. So some of this derivation later is going to feel a little bit ad hoc, because the key problem is you have to kind of guess which things to superimpose to get your boundary condition. So there's going to be one little step in there that's going to feel ad hoc, where we just assume hypothetically, what if my wave here takes on a particular form? And then lo and behold, you satisfy the boundary conditions, and then that's it. You call it done. So that there isn't exactly a way to start from the geometry and get a solution, but what there is a way to say, if you stumble into it by being clever and guessing and it satisfies your conditions, then you have your answer. So that is how some of these derivations might feel. There's going to be a step or two where we're just going to pull an assumption out of thin air and just say, let's assume maybe our solution looks like this, and then it'll just magically work itself out. So there's no like deduction there. There's just that little spark of insight you have to come up with to make some of this stuff work. Okay, but that's the final quiz question. So again, you don't necessarily have to include all of this stuff I wrote, just that general train of thought where here's my initial equation, show that it satisfied this thing here following these little steps. So it looks a little more awful than it is, but you notice it's just derivatives on top of derivatives, and we are nice to ourselves by singling out, say, one polarization so that some of this stuff goes to 0, and then you get a nice straightforward answer here. So I hope that was relatively straightforward to follow along, and it's just an extension of what we did before. Again, we had that same question. Here's a wave, does it satisfy? And if you get a true statement, you're done. You have a solution.
Just to clarify, where we started and where we ended. We started with the equation. What was that equation called? It's the,
which one?
It's just a general form of a wave vector. Is that correct?
So the wave vector is this thing here, this k vector, indicating the direction of your wave. This is a uniform plane wave. That's actually a good question. Let me write this down. Let's see, I have a little space here. You have something with the form of E naught e to the minus j k dot r. So that's this kind of in a more compact notation. And then there's some polarization. We call that a uniform plane wave. So that's kind of a buzzword you'll hear a lot. So I'm glad you asked. But anytime you hear uniform plane wave, it just kind of refers to something like this. Oops, sorry. Some mathematical function with this general form as a complex exponential representing a wave just propagating down in some particular direction. So you notice it's infinite along this direction and it's infinite along this direction, but there's a phase kind of progression along that direction. So this may feel a bit overwhelming at first if you're not. Some of you are probably going to be kind of like, okay, I can follow that. And some of you probably have a lot of cobwebs in your vector calculus and PDEs that's going to make it a little bit of a struggle. And that's okay. I just kind of want you to follow along and get that general sense of, I started with this and I showed it satisfied that. So that means this is a solution, which means any random polarization of this is a solution, and any linear superposition of solutions is also a solution. So a lot of very useful stuff just falls out of the math once you draw this little connection here. Okay, and I think that's about all we have for today. So if there's any other questions, you're welcome to ask and stick around. Oh, just gonna say, I'm gonna try my best to put up a few more videos by the end of today, and you should be able to watch them by Wednesday. And we're gonna start getting into the parallel plate waveguide. And I'm still really struggling to come up with just good homework problems, because at the moment we're just like neck deep in vector calculus, and I don't necessarily wanna browbeat you too much on the mathematical. So I might have like one or two little derivation style questions. But I was debating if it should be homework or just in class. So I might throw in a couple of homework questions that are just similar to what we've done in class. But a lot of this waveguide stuff is just very mathematically hectic. So there's probably going to be a few MATLAB questions like, here's a solution to a wave. Now just add a few more and see what happens and see if you can render an image in MATLAB kind of stuff. because the actual results for the waveguide stuff with, you know, the waveguide cutoff and the phase velocity, they're actually like these tiny little simple algebraic expressions. So we have this huge gulf between very, very simple trivial questions like calculate the cutoff frequency of this waveguide, which is one little algebraic expression, versus prove that this is a solution to the waveguide. There's no in between there that I can think of at the moment. So I hope you'll bear in mind as I try and figure out a good homework assignment for all this stuff. And thank you for your patience as well as we go through. And I appreciate all the feedback that you guys have been giving me. And I'm trying my best to kind of update as we go. Yeah.
I have a question. So I have like less than 10 minutes before class, and the first problem took me 15 minutes to put the equations in, and I don't see how I'm going to get questions 2 and 3 done. I just don't think.
So you're saying you don't quiz
the quiz is not set up right. I feel like it should have been like maybe take a picture of following along or something.
I should have said you're more than welcome to take a picture and submit it. You don't necessarily. The essay allows you to do a picture upload, doesn't it? Or does it not?
It actually doesn't. I tried.
That was my fault then. Sorry. Let's see. I can either update it right now to be a picture if you prefer, or I can just extend the deadline if you'd rather leave it as that and just type up some things. What would you prefer? Both are okay with me.
But if we're already inside there, then it's not going to update it. Like we'll have to submit it, and your updates will come later. If that makes sense.
You can upload images into those text box.
Yeah, I thought you can upload an image. Yeah, you can embed an image.
How do you do that?
So how you do it is when you're on the text box, you'll see that like list of things. And one of them will be like embed image, and you can click on that. Then you go to the Canvas tab on it, and then you can upload to that.
Yeah, I'm sharing my screen right now. So this is what it looks like where you type in answers. You see it says upload, embed image.
Oh, you can also do the 2 over is another option.
Because the Canvas upload, it seems like you can only upload like pictures.
And then you can do Canvas.
Let's see.
So Canvas on that top tab, and you can upload a file, and then you just scroll down and hit done.
Oh, okay. So it looks like it's a few annoying extra steps, but you can just take a picture and upload, it sounds like. Is that accurate? And if you like, I can extend the deadline to like 5 o'clock, just in case it turns into more of a headache. And I'm not expecting much, just, you know, a general sense that you followed along and got kind of the A to B.
Oh, I think I got it. So you need to upload like a file on Canvas, then use a picture on Canvas to like attach that picture to the quiz, right? Is that what you mean? I mean, Henry?
That's what it looks like.
Yeah, that's what you're supposed to do.
Okay, cool. Yeah, I think I got it.
Let's see. Where's a picture? If I just drag and drop, oh, it definitely doesn't like that. So you can upload. You'd say choose an image. It looks like you can just do a straight upload like here, right? Oh, then you're gonna have to kind of crop it. It looks like. Boop. And you say crop. Upload and embed. Okay, so it's a few annoying steps, but there it goes. So that'll allow you to upload real quick as well. But yeah, if you prefer, I can just make these straight up image uploads or file uploads, if this is like a giant pain in the neck. But I'll go ahead and extend the deadline to like 5, just in case you want to type something up a little more neatly. Does that sound fair?
Yes.
Yeah, I just want you to follow along and kind of get the gist of that derivation. Okay. No, thanks for pointing that out. That's all these little quirks of Canvas where I think it's going to work and the little details jump up. Okay, but that's all I got today. So keep your eyes out. I'm hoping to have some stuff uploaded by tonight for Wednesday, where we just jump into the derivation of the parallel plate waveguide. And I'm still just struggling on what will make a good homework question, because the book just has like massive derivations and proofs and the suggested homework there, which maybe a couple, but we want to do some practical stuff too. So just bear with me on that. We'll have some good practice problems. All right.
I guess a quick question. Kind of this has happened in 3300 as well, this derivation of the telegrapher's equations and now wave equations.
Mhm.
Does this does this continue to reappear in further classes, I guess? The derivation seems to get reiterated over and over and over. It seems like this is kind of something.
Yeah, if you take
You know.
antennas, you might rehash this stuff a little bit again. I guess if you take microwaves too, it'll be assumed you kind of know most of this. There might be an advanced EM class where they'll kind of refresh some of this as well. I don't know, does it feel like it's a little repetitive? Like you've seen this before and you're getting bored now?
No, not exactly bored, but I just wonder because usually in my engineering classes, what we've done is we've used the heavy mathematics to derive very simple, understandable relations to our circuits, and then we apply those relations to our circuits kind of in a blanket manner.
Mhm.
And so, I mean, these very difficult PhD level mathematics turn into like, hey, here's Ohm's law. Hey, here's conservation of energy. And these are kind of elementary principles we apply as in practice, I guess. But it seems like I guess I wanted to know what I'm in for, I guess. If I go into optics, if I go into antenna theory and whatnot, how much mathematics is in that, I guess?
They'll do their best to try and like start from the broad stuff and bring it down to kind of sort of the simplified practical things. You kind of have to remember though, like there's a broad audience of students in those classes. Like some of you are just going to go off and design antennas and not really delve too much in this after that. But then there's also going to be like 2 or 3 of you in that class who might go on and get a PhD and really need to know this stuff in great detail. And it seems like the teaching philosophy is kind of like, we can't really draw that distinction yet. Some of you might, some of you might not. So we kind of say, here's the basic foundations of it all. And then we're going to go into our applications. And then as you kind of decide for yourself if you're just going to go straight into industry or go more in PhD level stuff, you'll at least have that foundation there as you go. Does that sort of make sense? Like that's kind of a big struggle in just any sort of teaching philosophy of, how do you break it down in terms of here's just the stuff that the antenna engineers are going to need to know to go to work. And here's the stuff that the PhD level people will need. And then here's kind of the blend of things in between. And it is kind of a balancing act there. So for this class, I guess I'd say my philosophy is just say, here's the mathematical foundations. I'm going to make you go through it a little bit, but I'm not necessarily going to browbeat you and test you on it later on.
Oh no, I didn't mean that. It's just picking up from your kind of understanding of vector calculus. You seem to, I don't know if when you took EM for the first time, when you took Microwave 1, if you had a refresher course of vector calculus further down the line and you're like, wow, this makes total sense now that I've taken a refresher course on vector calculus for the second time or something.
That's been kind of something batted around actually, to have some kind of refresher material on this. Like one of the reasons I was hired for the department is to work on these training videos, which kind of had to get paused so I could teach this class instead. But that was an idea, is like, what if we had just simple little self-contained videos saying, here is some basic vector calculus. Here is what curl means. Here is what gradient is. And here's some nice pictures to represent. Here are certain identities we're gonna need. So that way, like the supplementary stuff would kind of be there for those who need it. But if you're already familiar with it, say, then it wouldn't necessarily be a requirement. So that sort of stuff is actually on a lot of people's minds, and we'd like to implement that sort of thing someday. Me personally, I worked as a TA for the math lab at BYU for like 2 years. So pretty much all day, every day, I was getting just math tutorage and refresher of all of this stuff. So for me, a lot of this was relatively straightforward, but I was lucky because I got that constant refresher of just helping other students through their calculus classes as well. I also think this stuff is super duper cool. So I'm kind of like naturally, intrinsically motivated to get into it. Some people may just kind of roll their eyes and say, oh, slog through it to get done at the end of the day. But that was my experience with this particular stuff. So even then, I remember kind of struggling a bit But that's mostly because BYU did not require a class in partial differential equations. So when I took this stuff, it wasn't the vector calculus per se, it was the PDE stuff that kind of killed me. So I actually think you're probably in an interesting position where you at least got the vector calculus and you kind of had that introduction to PDE. So you should be sort of familiar with how, you know, separation of variables works and how, you know, solutions to PDEs are kind of this ad hoc guessing a solution and seeing if it works kind of idea. So no, that's interesting. That's actually good feedback because the department will eventually kind of consider what sort of supplemental materials can we put up to make this stuff easier. So if you have any thoughts on that, like feel free to email me later, and maybe in the next semester or so, I'll be able to put some of that together.
No, thank you for the explanation.
Yeah, sure.
Not to discourage you, but in industry, I see stuff like this on my coworkers' whiteboards in their cubicles, and they're working through problems all the time. So we're engineers. We should not be afraid of mathematics. It's not something we just have to get through to get our degree.
Okay. No, that's a totally fair point. I'm at the PhD level, and I don't know necessarily how much my delving into this reflects what you would be doing at L3. So that's good to know then. So but then the question is, what's the best way to kind of introduce it, I suppose. So we'll do our best to work that balancing act.